Okay, thanks, Nikhil, and to all the other co-organizers for putting this on. This is going to be about repeated or dynamic matching games. I stole this subtitle, I think, from some of Ariel Pecos' work. He's here in Cambridge. So it's going to provide at the end of the day an estimator, but the theorems aren't going to be about taking the PLM of some sort of estimator. So it's really about outlining the theoretical framework and then providing an estimator for it. The co-authors, I should mention Pauline Corblet, who's on the market. She's been a postdoc at Luxembourg and is going to be an assistant professor at NYU Abu Dhabi, and most faculty, at least, have probably heard of Alfred Galichon at NYU. Okay, so is this the right computer to advance the slides?
Yes.
Okay, so the goal today is going to be to make some existing static matching games dynamic. So I contributed to estimating static matching games. Other people in the room have, and what we're going to try to do is make these models, or some subset of them, dynamic. And the more practical goal is to estimate models using panel data on changing relationships over time. Today, we're specifically going to be studying transfer utility matching games. If you don't know what that is, it should become clear. Okay, so I think it's pretty evident that relationships change over time. In labor markets, often people are switching firms. It's particularly important, say, in the tech industry, when people might carry particularly valuable skills between firms, and there's a lot of talk every off-season about professional athletes switching teams. I've worked on supplier assembler matching. When Apple switches its supplier for a particular component, since Apple's such a high value and volume company, that gets big news. The funding of startups also happens over time. So startups go through kind of a life cycle. They get different rounds of venture-backed funding. You might be attending like a very early accelerator program, getting seed early, later funding. And it could be potentially that different venture capitalists are involved in different rounds of funding. And finally, we all are familiar with normalized personal relationships, and you often, are in different relationships over time. You can get married, divorced, and then remarried. So the main idea is that these relationships you make today affect your payoffs from and attractiveness to other partners in the future. And mathematically, that's captured by a state variable that's sort of capturing your current situation. And so think about the labor market example. So we have workers who are getting experience, and they might be getting experience from on-the-job training or and so forth. And that is going to affect their state variable and might improve their match opportunities in the future. One of my co-advisors, Lazier, had this paper about entrepreneurs who are people who are and have accumulated a wide range of experiences. Supplier assembler matching, you can think about if you match with a particularly demanding assembler, that might cause you to improve your quality and do better in the future. Funding of startups, we don't think that the venture capitalists are just providing financial support, but they're also providing managerial advice, so that might causally improve your business plan. And then in personal relationships, we come up with several stories. One might be that if you get divorced, there's some stigma about you compared to people who have never previously been married. You might, on the other hand, more positively learn about relationships and how to avoid mistakes. And often relationships lead to children, and that can obviously affect your status on the marriage market. Okay, so so we're interested in extending static matching games. So what are static matching games? I think the way I think about them is that it's a competitive market for relationship formation. So if there's many startups relative to funders, then it's going to be hard to get your startup funded or to get this quality venture capital advice. That there's a bunch of high quality suppliers out there, they're going to take the matches and profits away from the low quality suppliers. So, of course, in a static model, you don't consider the features, you don't consider how your matches today are going to affect the type of matches you can receive in the future. So our dynamic model is going to incorporate agent state variables that describe your situation today, and they're going to affect the evolution of your agent state variables into the future. If we were to translate that term state variable into the language of static matching models, we would call that the type of the agent. And then there's forward-looking agents. So these are agents who are going to consider future matches. So to our knowledge, we're not just providing an estimator for an existing theory model. We're going to outline a new theory model. And so we're going to call it a repeated matching game. And we view it as a dynamic version of Shapley-Shubik. If you don't know that paper, that's fine. Plus, sort of thinking about a continuum of agents. And there's going to be a matching market each period. It's a transfer utility one-to-one matching model, somewhat wider for simplicity. And the matching market is going to clear each period. So what does that mean? Each period, there are going to be matches, transfers between matched agents, and then flow profits being realized. Then what your match partner is going to affect the evolution of your state variables. And then next period, you'll have a new state variable value. You'll be another matching market, new matches, new transfers, and new profits. And so you maximize the present discounted value of your lifetime utility. And, as it stands, if there's no frictions in the model, you might envision the model is going to predict a lot of switching. If you want to put in some stickiness, one way of doing that is with switching costs. To get back to skip to the end of the paper and think about econometrics, one thing, this current version, I have one or two slides about it, but one thing that we're not really dealing with in this version of the paper in terms of estimation is time persistent unobserved state as an alternative explanation for stickiness. Okay, this is not a search model, as in this huge literature in macro and labor. It's very influential. So the difference, I think, between a repeated matching game and a search model is here, there's a time period is when you make an entire match, and then potentially the match gets resolved. So I think in a search model, a time period is kind of the time you take to go to a job interview or on a date or some other sort of thing. Here, a search, time period is an entire, market opens and closes. And there's complete information in this model. And unless you put in frictions like switching costs, they're not inherent to the mathematical formulation. And the solution concept we feel is taken directly from the transfer utility literature on static matching games, which is competitive equilibrium. So again, I think the main difference is that search is thinking about shorter time periods than I am. Okay, so we have these influential papers. All these people won Nobel Prizes. Many other people have contributed to this literature on static transfer utility matching games. And our goal is to try to extend these to dynamic matching models. So we'll prove that a competitive equilibrium exists and can be computed using a social planner problem. So this is very analogous to one of the main results of Shapley-Shubik. And then we'll try to distinguish between this full competitive equilibrium, where the aggregate states, or the distribution of, say, workers and firms and what types each worker and firm have, can change over time in this economy, and a so-called stationary equilibrium, where individual workers and firms have their states changing, the distribution of workers and firms remains the same. Okay, so also in terms of when we add econometric errors to the model, we need to add these to fit microdata, where we see a lot of the typical theory that econometric error predicts a lot of zeros. That type of match will never occur, but we see data don't reflect that, so we add additional heterogeneity to the model to rationalize the data set. And so we add these econometric errors, and because we're adding kind of logit errors, it's going to look a lot like John's paper on dynamic discrete choice models with forward-looking agents and state variables meets this paper on family economics by Chu and Xiao on estimating static matching games one-to-one. So the type of agent in the Chu and Xiao paper, if you know what that is the agent state variable in John's paper. So, so we're exploiting, again, and some of the simplifications for get rid of integrals and that type of thing that everybody does, where we're using the logit. And so to think about it, that discrete choice that you're making each period is the partner that you match. Okay, so of course, Bob and many other people worked on discrete choice models as well in the 80s. Some other important work is on estimating static matching games. I did some stuff on that. I think other people have as well. And one of the estimators we're going to propose is MPEC. So this is where you do a constrained optimization of some statistical objective functions subject to some constraints. And my late co-author, Pauline and Pierre Dubé and others work on, Ken Judd obviously working on this topic. And then another computational approach is kind of, particularly new here. I don't think it exists in the economics literature, and I'll try to explain what this is towards the end. Okay, so kind of more narrowly, I've been working on this for a while, I gotta say, so this is kind of superseding some ancient work that I did, but you can still see this on my website if you're super bored during the talk here. But there's some papers on 2 period models of matching, where you invest, maybe match to a school in the first period, and maybe you match to a job in the second period. And then there's a couple papers, Eugene Chu and Marcin Pesky, about some type of search or matching model where there's dynamics going on, but there is exogenous separation only. So you don't, so some match ends with some probability when you don't leave the match voluntarily due to some endogenous market conditions. And then I think a lot of the co-authors of this final paper are actually co-organizers of the conference. So this paper on used cars has a fair bit of overlap with what's going on here. Okay. So the time remaining, I'm just going to talk about the following topics. So again, I want to outline this new theoretical model of a repeated matching game. And I'm first going to do it in kind of going back to Chaplin and Shubik in a model without econometric errors. Okay, then I'm going to stick in the econometric observables. That's not going to be a lengthy section. It's just going to kind of try to go through that quickly. Then I'll talk a lot about computation. So how do you compute first this equilibrium that's time varying? So you can think about there being kind of a distribution of workers and a distribution of firms, and those are changing over time in the aggregate due to all the matching going on. And then in some sense, a special case of the time varying equilibrium is a stationary equilibrium, where if you start in one period with some aggregate distribution, even though individual people kind of shuffle around and change the individual states, the overall distribution remains the same. Okay, and then when we focus on the structural estimation part, we're usually thinking about for computational simplicity the constant stationary equilibrium case. And so we'll talk about that. And then there's a very brief, for this purpose of this presentation, application to geographic mobility for Swedish engineers. Okay, so here's the model. So this is just going back to that simple model without econometric errors. So hopefully people who've been going to this conference all week, you've seen similar notation for other types of matching problems, although I can't say for sure. So we have workers and firms. So we'll just be the example today, going back to the empirical application at the end. So we'll call X, who lives in some finite set, capital script X, the worker state variable. Okay, so that's also going to be called the type of the worker, and those two terms are interchangeable. Okay, and again, it's a finite set. Again, that's for simplicity. Alfred has a paper in JP on continuous types in this logit type of world or something, but we'll just think about it as finite. Okay, and then again, just similar to other papers on dynamics or matching, you can think about there's some underlying continuous concepts perhaps, and maybe a vector of them, and somehow they got discretized and put into this finite type space. And then we'll have the same symmetric type of type space, capital script Y for the firm state variable, and it'll be lowercase y will be the individual type of a firm. And then, I'll use firm and job kind of interchangeably, so we're not going to think about many one matching or complementarities between workers. Again, that's for simplicity. I don't think there's anything other than in computation that's a hurdle to extending to that case. So there'll be an option 0, which is the option of being unmatched. Okay, so that's pretty common in these types of models. And then, so we'll call capital script 0 will be the union of this option of being unmatched and all of the firm types, and those are the choices that a worker can make each period. So, and the choice set of a firm then is capital script X0. It's the union of all the worker types that firm can hire and the option of being unmatched. Okay, so we're going to have an infinite horizon model. We've had some finite horizon stuff. I don't think things radically are different. We'll drop time subscripts where possible. This is the Rod-Bellman's equation without the t subscripts floating around everywhere. And but that doesn't mean that if I don't have a t subscript, that something is not varying by time. I would think about if you don't know if something is varying by time, it probably is varying by time. So the evolution of agent states. So agents have a match. That match is x, y. Okay, a match between worker X and firm Y. Okay, and then we're going to have this, and then this is similar to dynamic discrete choice models. We'll have a transition matrix for both sides of the market. So we'll have a capital P be the transition for the worker of firm X and firm of type Y, and then the P of X prime conditional on XY will be the probability that I'm in state X prime next period, given that I'm in state X today, I'm worker X, and then I match with firm of type Y this period. Symmetrically, Q is the transition rate for the transition rule for the firm. It tells me the probability of being in state Y prime next period, given that I was in state Y this period and matched the firm X in the current period. So, examples of this. So we have a worker who has some general human capital, and that might evolve if you are employed and not unemployed, or it could be some kind of occupation-specific human capital that only evolves if you're matching to a firm Y that has hired you for that particular type of job. In venture capitalists, Y could track the number of previous investment deals that you've done, and it would evolve if you undertake a deal in the current period, or it could track the experience you have in different startup sectors, which would evolve only if you make a deal in that particular sector. Okay, so we have an aggregate state. So this is critical to a lot of things, and it's a little different from, it's always less emphasized. We're going to emphasize more than in a static matching model. So we're going to have an aggregate state, which is going to be a vector of masses of each type of worker and each type of firm. So there'll be a continuum of workers and firms. M will be the mass of all workers. Capital N is the mass of all firms. And then MX will be the mass of the workers of different types. X, sorry, I'm going to advance the slide without meaning to. And M will then be the vector of all of these MXs, the mass of each type of worker X. And NY will be the vector of masses of all types of the scalar, that's the mass of firms of type Y, and then N will be the vector of all the NYs. And so at the beginning of a time period, what we start the per period market with, we have an MN. Okay, a tuple, or M is the vector of all the worker types, and N is the vector of all the okay, and then so each period there'll be an outcome, and the outcome will be a match, right? So the match here is a mass of matches between the two types of workers, the worker and the firm, X and Y. So mu of X and Y is a mass of matches between worker X and firm Y. Mu of X is 0, then is the mass of workers who are type X who are unemployed, and mu 0 of Y is the mass of jobs of type Y that are unfilled. Okay, and then we can collect, if the symbol mu appears without any subscripts, then it's just a vector matrix of all of those masses. And symmetrically, then WXY is going to be the monetary transfer or wage paid by Y to X. Okay, again, we're going to collect those into a matrix or vector W. And we get to the estimation part, similar to a lot of the work and dating all the way back to Becker. We're going to consider having data on matches, but not on okay, so then we have infinite time horizon. There'll be a competitive equilibrium, which are going to index these wages and matches by the aggregate state. So if the aggregate state is MN at the beginning of the period, we'll say in this competitive equilibrium, the wages are going to be W of MN, and the matches will be mu of MN. Okay, and then these aggregate states are going to transition according to applying the individual worker and firm transition rules to the aggregate states. We can include other aggregate states that aren't specific to an individual worker or firm, like some kind of demand shifter or something for some industry, but that's not in the notation. Okay, so the worker is then going to maximize the present discounted value of lifetime utility. That's going to be composed of the per period flow utilities. So the flow profit of a worker in a given period is going to be some kind of structural object, alpha xy, giving us the non-pecuniary preferences of the worker of X or job of type Y plus W of X and Y, this financial compensation that's in the equilibrium paid to the worker. It's going to depend on the aggregate state of the economy. So this is the notation for the present discounted value of lifetime utility. We're summing up over future time periods, discounting by the future and including the flow profit for that feature. Yes. It could. I took it. Well, here I'm thinking about infinite horizon, and so it's easier to think about time not entering structural objects. But you could, and a finite horizon model particularly would be very easy to add time to the structural object that you're trying to estimate.
So the main motivation for there to be dynamics then not in the long, so if I'm finding long and steady state is the changes in the composition of the types on each side of the market. Is that right?
So in the talk that I'm giving today, I'm focusing on endogenous changes in the types due to matching and the evolution of state variables. You could also put an entry and exit, and that would be kind of like a kind of auxiliary equations, some extra notation to keep around, where different agents are coming and leaving. But I think that's pretty straightforward. It's extra notation, but it's not conceptually that much more difficult to think about. Yeah.
Just a follow on that. So I'm just trying to understand if it's complete information. Why? What are the dynamics coming from? Why is it there in the first period itself? Just stays that way.
Can you repeat the question? I can speak up. I have bad ears.
So if it's complete information, right? There's nothing. You're not looking for anything. You're not searching. Why doesn't the equilibrium just stabilize in the first period itself? Why doesn't it collapse to a static?
Okay, so I don't want to use terms like unstable because they don't really have a meaning. So I'll say, there's a competitive equilibrium, and without further restrictions, I haven't made any assumptions about this P and Q. If everybody had one match this period, and then the P said, your state's going to be completely different next period as a result of that match, then your state's going to be completely different as a result of your match. So there's no mathematical reason for, in general, if we have a particular set of matches today, I hit it with some arbitrary transition rule that some other, completely the same thing happens next period. No, something completely different is more than likely to happen, right?
So just to clarify, when all of those, you anticipate everything perfectly. That's complete information, right? So
we don't. Okay, I meant to be clear. The transition rule P and Q are stochastic, are probabilistic. So it says I have a probability of being in a future individual state next period. What I'm anticipating for, in the current framework, there's no, as I said, that there's a minor statement saying I could add that, but for now, the aggregate state evolves deterministically according to some time series process that's given by the equilibrium to this model. Okay, but the individual states are evolving stochastically due to the uncertainty an individual worker or job is facing. And they're captured by these state transition rules that are probabilities between 0 and 1 rather than 0 or 1. So if I could have, I had a match with MIT last year, and then maybe my state variable is how many papers I publish, but there's some journal editor, there's some uncertainty about whether my paper is going to be published or not. So I could have bad luck and have no papers published, even though I was at MIT. So, so there's individual uncertainty about your individual state variable and how it evolves. But because there's a continuum of workers and firms, I don't know where I stated that, but there's an infinite number of workers and firms. All that kind of individual heterogeneity gets washed out, and then the aggregate state evolves according to some time series process. This M and N. M is the vector of worker type masses, and N is the vector of firm type masses, and those change due to the transition rules P and Q. Now, in a minute, I'm going to prove there exists a stationary equilibrium, and in that case, that doesn't happen like it's described. So that's a slight confusion, but in general, there's a full equilibrium where this time variant thing doesn't. Okay. Okay, so I'm just thinking about what expectation is being taken with respect to here. All these things in the future about your individual state are random variables in your individual match, right? So if you don't know your future state, as I just said, because that's uncertain to you, the expectation is with respect to the unknown future about your own career and your own future matches, which are taken with respect to information you have in the current period. Okay, so then we can write that worker problem recursively using Bellman's equation. So this is just the continuation profit on the left-hand side. On the right-hand side, it appears as well as reflecting the future payoffs if you're a type X prime X period as a function of matching with Y. So in the current period, so you're going to have a worker type X who's going to enter during a period where the aggregate state is M and N, a vector of worker types and a vector of firm types. This aggregate state, then I'm going to take the optimal match for me in the current period, which is going to maximize my flow profit, including the endogenous wage I'm being paid as a function of the current period wages, which are equilibrium objects, and then the discount factor times the expectation over an X period state, which is X prime, which involves the transition rule for my state as a function of my match, the job I have Y. Okay, and then I'm also going to here put in the deterministic transition for the aggregate state in my calculation. So, okay, that's relatively straightforward. And there's a symmetric set of notation for the firm. So the firm has a structural flow profit, involves paying, a structural object gamma that depends on the worker, the firm object, but the amount of output that the worker is producing minus the wage being paid to the worker. Okay, and then we're left with this Bellman equation for the firm, which looks very similar. They're going to pick a worker or the option on leaving the job unfilled each period, and that's going to affect their evolution of future states. And so then we can define a competitive equilibrium to just be for each of these aggregate states, the overall economy state, there's going to be a vector of matches and wages. And it has a property that if matches are occurring more than 0% of the time, then the matches have to maximize the profit of the two sides of the market involved in the match. So the job picked by the worker of type X must maximize the worker's profit for that period, and the worker hired by job of type Y must maximize that job's present discounted value profit. So this competitive equilibrium then is going to induce this deterministic time series of these aggregate states, M and N. So the aggregate states are going to move around according to this equilibrium, and individual states are going to move around, and people are going to reshuffle in kind of a more complicated way than in the aggregate. Okay, so the theorem, and this is our version of what's in this paper, Chapley and Shubik, 1971, is that the matching policy in this competitive equilibrium is going to maximize the social planner's problem. So the social planner is choosing the matches each period to maximize the present discounted value of economy-wide output for the sum over future time periods discounted appropriately, and then the sum within each time period, the sum over all the matches that can take place, and then we have the fraction of massive masses of that particular type occurring in that time period, and then the structural output of the matches that time period. Again, this is subject to the constraints you might think might apply to this type of problem, like, you can't have more matches of a certain type than there were people of that type to begin with at the beginning of the time period, and we have to respect the transition rules for the individual agents and states. Okay, so this is a pretty useful result. We can unpack it a little more and look at the Bellman equation version of that social planner problem. Okay, here's Bellman's equation for the social planner. So the social planner is just choosing these, it's a continuous choice problem, not a discrete choice problem. The social planner is choosing the match masses for each in a current time period of aggregate state Mn. The social planner is picking the matches, the matrix of match masses for all these different types of matches X, Y, and then again, we're getting this kind of flow fraction from the social planner's decision this period, and then there's some continuation value for the social planner. And the constraints are a little simpler now. I've kind of put the transition rules in the Bellman equation itself. And so we know from standard theory, the right side of this is a contraction. So therefore, we can show that there's a competitive equilibrium exists. And if it were to be some coincidence that two competitive equilibria existed in terms of vectors of matches, at least the vectors of matches would have to give the same present discounted value for y prime. Okay, and then as we know from linear programming theory, there's a dual to this, and the dual to this is written down here, and this involves cost minimization. And so we're trying to, at least mathematically, the dual says we're going to minimize the expenditure on the workers and firms, and subject to a bunch of constraints. And we recognize this one here is sort of like pairwise stability. Says that if some workers and firms who aren't matched wanted to get together, they can do better than what they're doing. And then this allows us to compute the equilibrium transfers. Okay, so to recap what happened, there's a deterministic time series of these aggregate states in this competitive equilibrium moving around over time due to all these matches happening at the individual level where agents and firms are moving around, workers and firms are moving around and switching their matches. Okay, so what you're doing is you're keeping track of all the other workers and firms in the economy, and what they're doing is you need to be able to predict the equilibrium of the wages and matches in the future. The economic skill or that competition is driving the matches that form, and so that's affecting both your current matches and your match opportunities.
Are these aggregate states exogenous and known as a perfect source set, or are they endogenous aggregate states that have to, some notion of rational expectations has to be imposed?
Well, they're equilibrium objects, but they're from the viewpoint of an individual agent, they're deterministic given the notation I'm explained here. I could add some type of shock or some other kind of macro type thing going on.
And so your definition of equilibrium is like a rational expectations then, or
yeah, so you're uncertain about your current state, but you're aware of the future state.
yeah, okay.
You're unsure of your your future individual state, but you're sure of the future aggregate state. But it changes. It's a whole time series. So the equilibrium is going to depend on these structural parameters, which other than kind of obvious things like the discount factors between 0 and 1, I have not restricted these parameters in any way. So that's good. And okay, so then of course this is a little complicated to have all these everyone keeping track of what everybody else is doing, and it's kind of looks a bit like Ericsson Takis or dynamic games in IO, or a lot of high dimensional state space. So one way of getting around this is to look at a stationary equilibrium. And in a stationary equilibrium, there's a constant aggregate state that says if the aggregate state starts where there's a mass of 2 workers of 16 years of schooling or whatever, then there'll be a mass of 2 of 16 years of schooling the next period. So the aggregate state remains the same, even though individual states are moving around each period. Okay, so a stationary equilibrium is when this constant aggregate state occurs plus in equilibrium, so that there's wages and transfers consistent with this. And so it's still the case that individual workers and firms are switching their states and that they're maximizing their present discounted value of lifetime utility. But now, since the aggregate state remains stationary, constant, then they don't need to keep track of what everybody else is doing when you take it to the computer. So then we can drop these M&Ns, these aggregate states, from the wages, for example, and from the Bellman equation continuation value. And then the worker and firm problem sort of simplifies. So we define a constant aggregate state to be that if matches occur with a positive mass, then the worker choice of firm Y is maximizing the worker's present discounted value by lifetime utility, and the firm choice of worker X is maximizing the firm's present discounted value by lifetime profits. Okay, and then this simplifies a lot of the calculations by dropping this aggregate state from, again, the continuation value and the equilibrium wages. And so if there's individual worker dynamics, then we go right down the worker and firm Bellman equations. They're pretty simple now. They look kind of almost trivial compared to previously, because some of the M&Ns got dropped off here. But we still should think about the wages as equilibrium objects. Right? They still arise due to supply and demand competition in the matching market. They still need to be computed, but workers and firms are the sort of best responding to them, and they don't change over time. Yes.
Chairman, I guess I was also confused over what Sanjay was asking. In the previous model, if the primitives remain constant over time, and the proportion of each type of agent, the economy remains the same. But why would there be a non-stationary equilibrium in the previous? Like, are all equilibria stationary? I guess that's what someone will ask the question.
For sure not. It took us, we weren't sure the stationary equilibrium result was true. So the generic case is where there's not a stationary equilibrium. In fact, the stationary equilibrium is sort of a special case of the full equilibrium. If you happen to hit the stationary equilibrium, you remain in the stationary equilibrium throughout. But if you don't hit the stationary equilibrium, then you're not going to remain at the constant aggregate state. So it's the generic case is definitely that the aggregate state is changing. I don't know. I mean, it seems kind of obvious to me. It's a little hard to explain. But say there's like 20% of people are in workers with type 1, 80% of type 2, and then if you it's only one firm type, but if you match to a firm and you're type 1, then there's a 0 chance you're type 1 next period, right? So then there's 20% of people, there's a no chance that there'll be a type 1 next period. And so it can't be a constant aggregate, right? So I mean, in general, if you just have some arbitrary distribution of worker types in the beginning of a time period, you hit it with some arbitrary transition rule. There's no particular reason why it would be the same next period.
I'm assuming there's some kind of ergodicity kind of assumptions on P and Q, or like all states communicate here, like, or
no assumption about anything. I get it's hard for me to get into your guys' heads because I don't see it's kind of the opposite of where I am, and so it's a little hard to see the exact point of confusion. But it's and there is, if you just hit some arbitrary set of vector of things by some arbitrary transition matrix, it's not going to be the same thing next period. Like it's not a property of math or anything.
The question is that there's an equilibrium assumption, there's an automatic assumption on the transition matrix, right? So is there an initial condition that is not an equilibrium, or is the initial condition free? I guess that's what the question is, that there are, you're restricted the transition matrices to have some optimality conditions, right? In equilibrium, the transition has to be optimal from each person's perspective.
Yeah, it's a definition of an equilibrium.
Yeah, and so
profit maximizing.
Right, and so if the initial condition does not satisfy stationarity, then I can see why, or it's not directly in equilibrium, then I can see why you have transitions over time and you don't have a stationary equilibrium.
Okay, so I'll agree with half that sentence. So forget about the sentence that said not an equilibrium, but certainly if the transition is, the initial state is not stationary, it's highly unlikely the next state will be a stationary equilibrium.
Exactly. Right. And so
I just think about it as we just plot this time series, right? This is the fraction of people of type 1, right? So workers of type 1, and here's time, right? So it's looking like this, right? Changing over time, and in a stationary equilibrium, yes. If we start this, if this happens, instead that there's some stationary equilibrium up here, once you hit that thing, then you stay there, right? So if we were to go up here and there, and then we would get there, then we would stay there forever.
Unfortunately, you have only 2 more minutes, so you can ask questions and you decide how you want to use your last 2 minutes.
Well, okay, so I'm just going to, so I guess I'll just try to talk about the briefly, and then if Harry can squeeze in a question, we can go over there. The theorem, stationary equilibrium exists, so we were proud of the theorem, but it's not a social planner problem, so it's a little tricky. So there's a lot of details here about the computation. Then we put in the logit errors, and I think this is pretty straightforward. Once you understand the previous stuff, if you were to go back and read a bunch of these other papers on static matching models, how to put in the logit errors, and so we proved that a stationary equilibrium exists for the model with logit errors, and the rest of the paper, a lot of it is about computation, particularly these slides. I don't think I'll have time to go over these things, but I think I would just try to sell this kind of as a practical conclusion. So the subtitle of the paper was an empirical framework. So two computational methods we suggest. One is MPAC, which is kind of, you're just maximizing kind of a likelihood subject to the equations that govern the model I just outlined. The nice thing about that is that it's very similar to computing an equilibrium in the first place. So once you figure out how to compute an equilibrium, the transition to structural estimation is almost, instantaneous. And this other thing, which Alfred was speaking, I've seen him present, he sort of starts with this bullet point 2 here, this max-min algorithm, and that's the main, mathematical novelty. And I agree, it's extremely helpful, but it's sort of less what everyone with this audience wants to hear about. But the that has the same property, right? So if we can rig up the objective function in this to put in data, and so the method of computing an equilibrium is very similar to the method of structural estimation. And so I think that's an advantage of this approach. And so we think it's very easy to take some microdata on panel data on changing relationships over time. Okay, so I wanted to let anyone who wants to speak ask a question. So Harry, do you have a question?
I'll chat with you.
Okay, I guess to keep on schedule, thank you very much.